Welcome to the ECS podcast. I'm Rocky Calvo, Executive Director of the Electrochemical Society. The purpose of this podcast is to connect the dots between the sciences, our everyday lives, and the sustainability of the planet. During the Electrochemical Energy Summit, which took place at the 228th ECS Meeting in Phoenix, Arizona, we had a chance to sit down with some of the leading researchers in the field of energy technology. In this podcast, you'll hear key speakers from some of the top energy research institutions in the U.S. discuss energy storage, changing the grid, and roadblocks for renewables. From solar critical issues to the growing global energy need, these experts delve into some of the most pressing topics facing the world today. Krishnan Rajeshwar from the University of Texas and ECS Board of Directors Senior Vice President is your moderator.
Okay, we are gathered here as part of the Electrochemical Society meeting in Phoenix. This comes on the heels of the summit we had the last couple of days, and we are fortunate to have four leaders in the area of energy storage, and I'm going to go around the table introducing them. First one is Paul Fenter from Argonne National Lab. He heads up the Center for Electrochemical Energy Science. The center is called CES. And they will talk a little bit about what their center focuses on in a minute. Next up is Gary Rubloff, and he heads up the Center for Nanostructures for Electrical Energy Storage, Energy Frontier Research Center, and this is based in the University of Maryland. And then we have David Wasilowski. His center focuses on the fluid interface reaction structures in transport. Acronym FIRST Energy, again EFRC, based at the Oak Ridge National Laboratory. And last but not least, we have Stan Winningham, Northeast Center for Chemical Energy Storage. So, gentlemen, thank you for taking time out of your schedule to be part of this podcast. And I'm going to ask Paul to say a few words about what his center does, and then we'll go around the table. Paul.
Thank you. Well, CES is one of the Energy Frontier Research Centers. Our center focuses on understanding the reactions that take place in lithium-ion batteries, and a big emphasis in our center is trying to both understand and control electrochemical reactivity. So our center has chosen three types of lithium-ion chemistries that we focus on. One is a relatively simple chemistry where one's inserting lithium into a lattice without disrupting it. Another one is one in which we're doing conversion reactions, where it's a more complicated reaction where the materials are changing, and which involves essentially lithium reactions. And the third is one where you involve both lithium and oxygen in the reactivity, which we refer to as hybrid reactions. And so in the end, there's a big focus on interfaces in the role of these reactions, and on the use of advanced characterization and computational tools to watch these reactions take place.
Thanks, Paul. Gary?
Yes, so I'm the director of our nanostructures for electrical energy storage. We call it NES, not to be confused with CES, Paul just talked about. And our focus is, I think, quite different from my colleagues here, because we really don't focus primarily on materials. We use typical materials that others have studied in some detail. And we ask the question how to arrange different materials together to accomplish the functions of energy storage. For example, if ions are moving in electrochemical storage, electrons have to be moving also. And if you're going to exploit nanotechnology, which is really what our mission is, you have to be able to structure those different materials together in individual nanostructures and massive arrays of such nanostructures. So our focus has been on individual heterogeneous nanostructure design for the first 4 or 5 years. And toward the second half of that period, we started thinking about the consequences of aggregating many nanostructures at high density, which would be necessary to achieve the power and cycling benefits. And that has led us into a path which we're now pursuing, which is to understand the consequences of architectures, how you put together zillions of nanostructures so that performance is good, so that degradation is minimized, safety is increased, and so on.
Thanks, Gary. David?
Hi, I'm Dave Weslowski. I direct the Fluid Interface Reactions Structures and Transport First Center. We're based primarily at Oak Ridge, but we have 8 partner institutions, including Paul Fenter at Argonne. Okay, so our center is really focused on fluids at interfaces rather than what's below the interface per se. And so that is really a paramount feature of capacitive electrical energy storage through the formation of electrical double layers where ions zorb on oppositely charged surfaces, and that whole process is very intimately associated with how electrolytes behave at interfaces, how their structure and dynamics change, how they are transported through nanoporous substrates. And of course, we get into redox-type reactions that are more akin to the behavior of battery systems. But our focus still remains on the behavior of the electrolytes and how the interfaces affect that behavior.
So I'm Stan Winningham from Binghamton University. That's part of the State University of New York. And I'm director of the Northeast Center for Chemical Energy Storage, NEXES. And we have partners stretching from San Diego in the west to Cambridge, England in the east. And we've put our center together to really understand all the reactions that occur in cathode materials within them, on their surface, and whilst those materials are actually reacting. So our goal is really to look at lithium-ion batteries and get them to meet their full potential. Most of them at the moment are only 25% of their full potential. So we look at layered oxides. We're looking at putting 2 lithiums into the materials where only 1 goes now. And we use a combination of theorists to guide the experimentalists and to check that our results are correct. But also we do a large amount of operando studies. So we look at actual electrodes as they're cycling, using facilities particularly at Argonne, previously at Brookhaven, and a little bit in England at the moment.
Okay. Well, I guess storage plays a role in 2 key application arenas, if you will. One was plugging into the grid, and the other is transportation. So I was wondering if gentlemen can comment on what the issues are and what's the state of the art right now, and what are the future challenges in meeting the requirements in the 2 areas. Paul, you want to go first?
Well, I mean, I think Stan's probably maybe the best person to address these things. He's been working on this for quite some decades. So.
Yes. So I've been involved in lithium batteries, I guess, for 40 years now. Yeah. Most people don't realize Exxon built a battery facility for electric vehicles. And this was in the 1970s when we had our first gas shortage. They eventually got out of that business, but I think the issues remain the same today. Is how you can put more energy into a given volume. And I think for vehicles and all your, can I call them toys, your iPhones, your iPads, is how much energy can you get in the volume. The weight is very much secondary for those applications. And right now, on a volume basis, we're getting less than 20% of the theoretical. So we have to probably replace the anode, but put far more lithium into the cathode. So things have progressed, but we've still got a long way to go.
Yeah, I think one of the themes running through a lot of the centers is this idea of, as you mentioned, is trying to get the full use out of the materials. I mean, there's a theoretical capacity, but typically when you get to a device, the amount that you're actually using is much less due to some issues, some side reactions, and so that's one of the challenges, is finding out how to make full use of these materials. I mean, that'll be a lot easier than finding a completely new material. Right. That may even be impossible at this point.
I think it's worth pointing out there's probably only been 4 materials in 40 years, so that's a tough challenge.
So one of the things that, I'm on a steep learning curve in our center because I'm a geochemist by training, but so we stumbled upon capacitive energy storage, and the key there is very rapid response time. So if you look at the potential, the line voltage during the day and during the night on the grid, there are enormous, very short wavelength spikes and sags. And capacitors can absorb that sag, or absorb that spike, or fill in that sag much more efficiently than a battery. So expecting a battery system to smooth out that kind of line voltage is kind of a waste of time. And if you think of the same thing in your vehicle, when you slam on the brakes, the brakes get hot. Well, wouldn't it be better if you slammed the brakes on and you charged up your battery or your capacitor with that energy? So, I think this is where capacitive energy storage dovetails with redox chemical energy storage.
Yeah, I agree, and I think that probably for the most part we're all on the same page with regard to recognizing that every one of these applications means I would like to have this much stored energy at a given power level. Mm-hmm. And so that means we have to be working between batteries and capacitors. Mm-hmm. And finding some way to put that together all in one would be best, but one way or another have to have both those functions.
I think this really merges when you shrink the active material down to the nanoscale. So you have both capacitive and redox energy storage, energy uptake, energy release, and they're very interactive. So as you change the redox state of the substrate, you change the surface absorption properties. So you get different capacitive behavior as you change the nature of the substrate.
In terms of technologies, I guess the lead-acid battery is a classic example of one which has been refined through many, many years. Almost you can think of a quiet revolution. I can still remember the time when I had to open the hood of the car and check the water level or the density or whatever, the acid. Now we don't even think about doing any of that. It's completely maintenance-free. Are we looking at similar quiet advances in these next generation battery materials, or where are we at in terms of?
Well, the thing that hasn't changed, though, is the weight of the darn thing. I mean, if you've ever had to carry your battery somewhere to get it charged, the weight hasn't improved any, as far as I know. Just the reliability.
I'd say something different. The initial hybrid buses used lead acid, and they had horrendous maintenance problems with them. So the maintenance has not gone away from lead acid. So, for example, BAE, who are based in Binghamton, have switched totally to lithium ion. So lifetime cost lithium ion is much superior to lead acid.
So I take it, Stan, you're not a big fan of lead-acid battery. You would rather see everything being switched to.
I have one in my car, and I know Arizona is not a fan, because I had a car here. Lead-acid batteries don't last more than a year in Arizona. They die because of the heat, and that's, I think, one of the issues with them.
Yeah. Plus, we have to worry about recycling and the toxicity and all that, too.
Yes.
And how about other possibilities in terms of technologies for batteries? Can we talk about that in terms of
I
what
guess
you guys are addressing?
I could say something about that from our NICE point of view. We work on what I would call evolutionary versions of batteries. This is using thick film technologies to grind up materials, put the materials in place as electrodes, and so on. We work on some of that, but in our piloting the scientific issues, we also use thin film technologies to be able to create highly controlled nanostructures. And these look a lot more like what you'd find in a computer chip or what you'd find in a liquid crystal display that you have on your laptop. And this would be a very disruptive way to make a battery, but it's one that we have in mind as a possibility in the future. So
What about
I wouldn't bet on it yet, but
What about 3D printing? I mean, are people thinking about fabricating battery structures?
absolutely. We actually have people at Maryland who have exactly that in mind.
Cool.
So that was Gary and David in the conversation.
Oh, yeah, we're on the radio.
Oh, yes, sorry.
We got to put ID tags on the voices. And so, Paul, you have any thoughts on materials, technologies, and batteries?
Well, I
Sure
think,
you
from my understanding, I think Stan probably can add to this, but most of the improvements that people have seen or think they've seen in batteries have actually been in the devices more than in the batteries over the years. So your cell phone lasts a lot longer, now that, on a charge than it did 5 years ago. But that's essentially because the cell phone is making better use of the power. So I think it was one of the indications that this is a really hard problem. Right, and we're up against some very stiff walls to where we're making advances. Is going to be is really, this is where DOE considers this as a grand challenge. I think that's why, because you're pushing against the physical limits and chemical limits of a lot of these types of materials. So,
Isn't that also a function of how much power or energy needs? I mean, it's very different for handheld devices versus, let's say, grid application.
Yeah, but if you go back 10 years ago, even 5 years ago, you didn't really put your laptop computer on your lap because all the electronics generated so much heat. And now they're just warm when you touch them. So all it's really the electronics where the major advances have occurred. The batteries are getting better, but they're getting a little bit better every year. But it's the electronics are not wasting the energy that the batteries
So does
provide.
that mean our challenge is to get on the Moore's Law curve?
No.
Just keep up with the electronics?
Yeah, but I think when you involve chemistry, which is what batteries are, there's no such thing as the Moore's Law curve. And some of us have calculated what the ultimate limit is for lithium-ion batteries. And it's about maybe double what we have today. And if you're worried about energy stored on a volume basis, you're not ever going to get better than lithium batteries. On a weight basis, yes, but on a volume basis, there are specific limits there.
So does that mean we need to look for other alternatives? We have almost hit the wall with lithium technology,
Well, I'm
ion
saying
technology?
no other battery technology can exceed lithium on a volumetric basis. On a weight basis, they can, but on a volume basis, lithium is pretty small.
Right.
yeah, I hope we don't have to go back to storing energy by pumping water up to our roofs or whatnot.
Yeah, well, pumped hydro is still
It's pretty efficient, right?
70% efficient and probably the lowest cost way of storing gigawatt hours of energy.
Yeah. So I mean that's one of the things we're competing against, right?
Yes.
That versus gasoline, for instance, which is incredibly cheap.
Yes.
So yeah, these are really hard problems. So, but
Well, let me ask about packaging, though. My understanding is that the useful capacity you get out of the battery is about half what it would be if it were just about the materials and their capacity, or something like that. Something like
You're overly
factor of two.
optimistic. It's about 20%.
It's 20%.
Yeah.
So doesn't that mean we've got 80% that we could work on
Yes.
packaging?
Yeah, and we look at the fundamental behavior of the materials. If you could increase the ionic transport, the electronic conductivity, then you could make the electrodes twice as thick, cut out half the separators, half the current collectors. So we need fundamental studies on the materials themselves to make them better.
Well, and I think fast charging and deep discharging have physical effects on batteries that kind of limit their long-term performance. And if you can overcome some of those, everybody's experienced this. Their cell phone holds a charge for a month or a week, the first week, and then 6 days the second week, and a day the 10th week, and so overcoming those kinds of problems is another big issue, especially for cars. That you want you want your car to work for 10 years without changing this gigantic battery pack.
That's the same issue. You want to increase the ionic transport, electronic transport, so you don't have resistive losses, so it doesn't cook itself when you fast charge and fast discharge.
So in the microelectronics area, all the industries and academia and national labs have come together to chart out. One of you mentioned Moore's law, and Moore's the forthcoming challenges associated with shrinking the dimensions. And is there some such similar? Are people working together here to address where we are going and with this storage technologies? Is there some common, I'd say, chart, if you will, or I think they have a word for it, a roadmap is what they call it. Is there a roadmap in the battery area that people are looking at?
Paul's probably the best one to answer that because it's probably going to come out of Argonne or DOE or something.
Well, I think from the Department of Energy, I think the applied parts of the Department of Energy, has a very clear idea of what kind of targets they want to make over the next few years, because that's the part of the Department of Energy that's trying to actually make the better battery. I think our roles, I think, with the Energy Frontier Research Centers is a bit more of a longer term vision of what is, trying to understand the limits of what's possible and what's achievable. And so, I think if the breakthroughs that we make now, given past history, I would say if things go well, they would be part of products maybe in 10 or 15 years from now. So, there's a long time between the science and when something shows up in your cell phone battery, for instance.
Well, on the other side of the coin is there's a very efficient, enormous industry out there who's really waiting for new breakthroughs to try to implement them and make commercial products. So, this is really different from geoscience. You can take forever to solve problems in geoscience, but in electrical energy storage, man, if somebody else picks up on it when you give a talk at a meeting like this, and they're making a commercial device before you can get the paper published. So that's a good thing in a way, and I think what the federally funded research is all about is providing, greasing the skids for that capitalistic process to operate efficiently.
So I'd like to comment on your question, though, about roadmaps, because, I come from a different field. I used to work in the semiconductor domain, and I remember the first meetings when this entire road mapping process started, and I was involved in it for quite some years. And I think it's a very effective way to try to identify directions to go and to set goals and to do pre-competitive research. That's what several industries, semiconductors, displays, data storage, not energy storage, have been. And I think that from what I perceive in the batteries world, the kinds of centers we have here, including the hub as well, I think are a very good replacement to get some of that collaboration and interaction to be effective. But I think it's an interesting question whether there's more road mapping of the kind of, let me say, the R&D pathways that we're pursuing to be able to actually write down shared goals. That would be interesting.
In a sense, DOE did this maybe 8 or 10 years ago when they had a whole study group on energy storage. And they addressed what are the major research challenges. And they mapped that out. And I think the EFRCs really came out of that study.
Okay.
But it wasn't in what we now call a roadmap
Yeah, right.
type.
But in essence, it defined a lot of the horizons on
Yes.
what the opportunities might be. And actually, it'd be interesting to go back and look at that again carefully. It's always interesting how well predictions actually match up on what we're doing versus what we thought we would be doing at that time.
Yeah, I guess, unfortunately, it doesn't seem to exist a similar effort in the energy conversion arena in terms of what the alternatives are, or at least the various parties are not coming together at the table and mapping out what needs to be done to transition from, let's say, fossil fuel technologies to renewables and what the implications
DOE
are.
has a pretty big program in energy efficiency and renewable energy, and the fossil energy program that are addressing those issues pretty aggressively. I think what you got to keep in mind is that combustion engines and burning fuels is pretty mature science. So it's not changing at as rapid a pace as the electrical energy storage front. But for instance, if somebody can come up with a very cheap and efficient way to convert methane and ethane to ethylene and methylene, that would be a true breakthrough for the materials industry. So we have all the methane that we know what to do with right now. In fact, we're capping off wells, but what do we do with it besides burn it?
I think the other big difference, semiconductors isn't a political hot potato. The energy, future energy, is you're putting coal miners out of business, you've got oil coming from overseas. I think it's a much more complicated scenario that obviously involves different states in different ways, involves far more people, how we run our lives. And semiconductors is kind of to one side of that. So I think there's a reason why the US doesn't really have a complete energy policy.
Or the world at
Or the
large.
world, right, yes.
That brings up what keeps you guys awake at night. Stan, you go first. I mean, in terms of what needs to be done. And
What keeps me
you
awake
can
at
talk
night?
about your own center, and you can talk about the larger.
It's this report needs writing, that report needs writing. How long late can I be with the report? No, it's things that keep you up at night are normal personnel issues. I don't think there's any big issues that keep me up at night.
That's a good problem to have.
Yes, and at my age, see, I've seen everything, so it's easier on me, I guess, than some of my younger colleagues.
David?
Well, a lot of the impetus, or at least the rhetoric behind putting a lot of research effort into electrical energy storage has been related to renewable energy sources. So you generate power from intermittent sources and you store it and then use it on a more even basis. But that has been also related to climate change. And there is I think, a fundamental lack of understanding by most people, including policymakers and even maybe science managers, about the staggering job it would be to replace fossil fuels with intermittent energy sources, and not just in terms of infrastructure or cost, but impact on people's lives. I mean, energy is life, and cheap energy means lots of life. And if you make energy expensive, then it has tremendous impacts on everyone. So I think this whole notion of, well, we're going to stop global climate change by eliminating fossil fuel utilization is really naive. I think adapting to climate change and slowing the time scale over which you need to adapt is the more intelligent way of looking at the issue.
Gary, you want?
Yeah, so what keeps me up at night with regard to this domain? I think policy interactions with research is a big concern, because public understanding of these issues, being informed about them, is always hard to capture people's attention. That certainly. I certainly lose some sleep either thinking about a big problem that we have to fix something in the lab, or something exciting like a new idea. That sometimes keeps me up. But lately, I've been thinking a lot about what is the trajectory for manufacturing some of the things that we make as prototypes, if they are good candidates in terms of performance. And I don't think we have a plan for that yet, for an alternative way of making batteries.
For myself, I think the things that keep me up at night are kind of the mundane things about one thinks you have a good idea, and then you're pushing on the research program, and there are a lot of things that have to come together. Invariably, I think what I'm finding as these things move forward, I'm finding that often the solutions are the things that I'm not imagining. And so, I'm relying on all the people in the center to come up with better ways of thinking about things. So it's sort of the gap between my sort of perception of what should be happening and what is actually happening. And in the end, it always seems to work out, but it's always, to me, that watching that happen, it seems to, it's kind of like the sausage making part of science. And it's both exciting and sort of dangerous at the same time.
So actually, this is probably the first time, at least in my recollection, that the Electrochemical Society has done in bringing centers, research centers together on a common platform in terms of a summit. I was curious in getting feedback from you all about how well this worked. What are your impressions, and how better can we do it in future? Is this a good experiment to get, or is it been a dangerous thing in getting all the people together on the same platform, if you will? Again, Stan, you want to go first as the?
Yeah, I think most worked well. I think there's some things we did this again, which suggest changes. I think we'd put all the directors up front on maybe the Monday morning, and then have the more detailed talks afterwards. And less competition with some of the regular sessions, because that bit into the attendance at times. But I think it was a good exchange. Certainly I saw my folks were listening to a lot of the other talks, and they don't really have that chance normally.
Yeah, again, this is a good problem to have. We faced competition from other regular sessions in terms of meeting and competing for the attention of the attendees, but all in all, I think, David, your perspectives?
Yeah, well, I have to risk preaching heresy, but next week, all of us are going to Washington for the Energy Frontier Research Center annual meeting.
2 weeks.
2 weeks. 2 weeks. Oh, thank goodness.
So this was a good dry run for.
Yeah, what I'm getting at is it's almost a duplicate of this symposium, for at least for the 5 centers that are involved in energy storage. And I'm wondering if there couldn't be perhaps a way for DOE to conduct their business in a more public format that would save us from essentially duplicating this kind of effort.
And we have done that.
I'll probably get in trouble. I know my boss is cringing right now. He hasn't heard the podcast yet.
Actually, that brings up a good point, Dave. We have done this, and we have done this in the solar area, where I believe it was DOE conducted their contractors meeting, if you will, as part of one of the sessions of the ECS.
Excellent idea.
I think it's possible to combine the two.
The only caveat is that, in this environment, it's a little bit more risky, especially because of the very competitive industry and academic research effort and development effort out there to talk about things that haven't been published yet. So at the contractors meeting, you can let your hair down and talk about new things that haven't come to complete fruition yet. So I guess there's pros and cons in either approach.
Okay.
Yeah, well, certainly I think that getting people together in this way and having somewhat coordinated arrangement of talks so that you can see, well, here's the spectrum of energy frontier centers working on this, here's where the hub is on this, and I think that was really very helpful. This has happened in other societies, and I think it's a healthy thing because no one society kind of owns everyone, and when you talk about batteries, Electrochemical Society is the first thing you would think about. So I think that was absolutely appropriate.
Talking about, I think, David, you brought up the point of sharing of information. Are industries a big part of your centers in terms of?
Not ours, but we are in close contact with people that are. I mean, capacitors is not a big industry. Okay, so it's just not doesn't have the global reach that battery-based energy storage. So I think in that sense we can be forgiven. So maybe I should just defer
But
to my
I think the
colleagues.
EFRCs are really fundamental to really pre-industry involvement. So we interact with industry, certainly with our organizational groups. In New York, we have the New York Battery Consortium. We tell them periodically what we're doing. But industry doesn't fund the EFRCs, and there's no request from DOE for us to involve industry. So I think, no, it's the EERE part of DOE wants the industry involvement. They want us to do really the more 5, 10, 15-year out research.
By the same token, are you all worried about flow of information from your centers to industry, maybe at a too premature stage? Is that a concern in terms of having, for example, these type of discussions in a public venue like the society meetings?
I don't think that we have that concern too much. We're usually careful about whether we've submitted for publication something that we're going to talk about. If there's potential patenting or intellectual property associated with that, we're very careful about that. So we pay attention to that. And the other trend that I've seen in our center and in colleagues who are at the same university and related to the center, though not a participant, is increasing attention and funding from the other parts of Department of Energy. This would be ARPA-E, EERE, and so on. And that brings industry much closer, usually. And I think it's healthy to see that because it kind of tells you where can you make an impact as well as a scientific advance.
Okay. Any final thoughts? Do we want to talk about funding? Because that's always politically, sometimes it could be. I mean, for example, I work myself in the solar fuels area, and through the years it's gone through ebbs and flows depending on the political winds in Washington. Is that true for the storage area as well?
No, this is an exciting area. No, so I've been in it 40 years. When I started, there was some federal funding, and it was probably mostly at Argonne and not much else. Then it went into complete lull when Exxon got out of it. DOE said, we're out of this business. Then it took them 10 years to get back in. Right now, there's probably more funding from the government and energy storage than that has ever been. So some of us are concerned this can't go on forever, and there'll be a turn down. But right now, the funding is very, very good.
So we don't have to be worried about who killed the electric car in that sense.
Well, it's going to be policy that's going to kill the electric car, not science, I think, at this stage. And if we had smarter politicians who put more of a gas tax on when the gas prices went down, so could fix our roads, we wouldn't have so much competition for low gas prices. Now, we have to look long term, and every time the gas prices go way down, funding tends to go down. There's less support, certainly locally, for wind, solar, and all those things.
David?
Yeah, I guess the one comment I would like to make is the energy centers and innovation hubs with a 5-year funded cycle initially, and a number of them, all of ours, have been renewed for another at least 4 years, we hope. This is a time scale where you can really plan long-term to do very fundamental science. And it takes a long time to teach an interdisciplinary team how to interact, how to talk to each other. And I showed that in my talk today. Our productivity is at its peak 6 years into the project. So I really do think that this is an excellent plan for funding fundamental research. I don't know how I would survive in a world where everything was 3 years and up. That would be very difficult for me. University guys might have more experience with that, but that would be hard.
But we can do high-risk research within the energy centers, which you can't
Yes.
do on a normal one year to the next year funding.
And it's even more compressed in the corporate world, where it's the next quarter, especially for publicly traded companies, where the CEOs are beholden to the public. They are worried about the next quarter, so that brings
But they
very
didn't
different.
used to be.
Well,
When
yeah,
I
I mean,
worked at Exxon, Bell Labs, DuPont, GE. They
right.
all had great corporate labs, and
Yeah.
they looked 5 or 10 years in the future.
Bell Labs was the model for the energy centers. That was the initial rhetoric, was establishing that kind of an environment.
Yeah.
Why industry has moved away from that, I don't know.
Yeah, we heard a fascinating account from Adam Heller, who used to be a staff in Bell Labs, and those were the golden days when a lot of the innovation was driven by the corporate world, including places like Exxon and the Bell Labs.
So some industries have recognized that. There's something called the Advanced Energy Consortium, which is directly funded by a number of major oil companies. And they are conducting very fundamental research. One example is they're trying to develop nanomaterials that they can inject into a formation and then either have that nanoparticle report back to them remotely or withdraw it from the geologic formation and tell you what it has seen. I think this is very, very fundamental, very creative science. And so there are some industries that are recognizing that kind of need. I'm not sure if that's true in the electrical storage industrial world.
I could make a comment about the question that you asked, and I agree with everything that you all just said. I think that the prognosis for continuing this kind of funding is better than it would be in most cases, potentially for two reasons. One of them is I think we've all experienced the kind of maturation and teamwork that develops where new ideas come out and new collaborations in a way that I've never seen comparable to this. If you have 5-year, 4-year, something like that commitment and the likelihood that you could continue that, the idea flow and the productivity is much greater than individual smaller grants. And I'd like to think the public is going to support that for that reason, but I'm not that naive. However, I've never met anyone who didn't say, I'm so glad when I told them I work on batteries. So I think we have that on our side.
So I guess a final thought in terms of you mentioned this critical mass. Does the return scale with the size? And I mean, there surely reaches a point where the rate of return is not commensurate with the investment, and one can point to big science, maybe fusion, where very large teams. I mean, you can make the argument you need the scale to achieve progress, but at what point does it stop becoming linear, or even reverse
Some
the
would
course?
argue the EFRCs are about the right size because you can effectively manage them without having a whole group of professional managers there.
Yeah.
I
Nope.
agree.
I stand on the fifth.
We won't go near the fusion issue. These huge programs.
Oh, we don't want to rain on the physicist parade. So I guess with that, really, it's been a wonderful discussion, and I'd like to thank you all on behalf of the Society for taking time out of your schedules to be part of this, and hopefully we'll see many more of these and maybe have you guys return to this venue in the future. So thank you all.
Thank you.
Thanks.
You can listen to more episodes of our podcast by searching ECS Podcasts on iTunes, or just go to our website at electrochem.org. You can also find ECS on Twitter at ECS.org. Thanks for joining us today.